Electricity and Magnetism. Lecture 2 by Azamat Orazbayev. Narrators Sabina and Alina Orazbayeva. Today we are going to study magnetic field and its properties. We will also study the relation between electricity and magnetism and look at various electromagnetism phenomena. In the last part of our lecture, we will learn how electric and magnetic fields are used in engineering. Let's start with the magnetic field and its properties. According to the Merriam-Webster Dictionary, magnetic field is the portion of space near a magnetic body or a current-carrying body, in which the magnetic forces due to the body or current can be detected. In our everyday life, we most likely can experience the action of magnetic fields generated by permanent and electrical magnets, and also the Earth's magnetic field. All these sources of magnetic field are actually arise from the ability of moving charged particles to generate magnetic field. Magnetic forces, which we can observe and measure, arise in two stages. First, a moving charge, or a collection of moving charges, produces a magnetic field. After that, a second current or moving charge responds to this magnetic field, and so experiences a magnetic force. We do not consider Coulomb's repulsion force between two positive charges. Thus, magnetic fields reveal themselves through the action of magnetic forces on moving charges, currents, and other magnets. The magnitude of magnetic field. Historically, the symbol B has been used to represent a magnetic field. We cannot see magnetic fields with our eyes. But a magnetic field can be represented by means of drawings with magnetic field lines. The direction of the magnetic field B at any location is the direction in which a compass needle points at that location. In other words, compass needles align along magnetic field lines. Magnetic field lines are like streamlines in a fluid flow. Properties of magnetic field lines. Magnetic field lines do not intersect. Lines are dense in places of high magnetic field and vice versa. Because there are no magnetic monopoles, and contrary to electric field lines, magnetic field lines are closed lines. It is a convention that magnetic field lines go out from the North Pole and enter the South Pole of a permanent magnet. The unit of magnetic field is Tesla. Let's consider the magnetic field lines of a bar magnet. We have a bar magnet with a north and a south pole. No magnet can have just one pole, since magnetic charges, magnetic monopoles, have not been discovered so far. We also have a vessel filled with a viscous liquid. The liquid contains metal swarf. These metal chips can act as tiny compass needles. Then the bar magnet is placed into the designated opening. When the bar magnet is inserted into the opening, metal chips start to orient along the magnetic field lines. Please note that these metal chips do not fall down under gravity, but stick to the magnetic field lines. After some time, metal chips will be aligned along the magnetic field lines generated by a permanent magnet. Magnetic field lines do not end at the South Pole. Rather, they continue to the North Pole inside the bar magnet, thus creating closed loops. This is why when a permanent magnet is cut in half, each piece has its own north and south poles. If you try to separate the north and the south poles of a permanent magnet, you will fail. At the moment you cut the bar, an additional south pole and an additional north pole will appear. Remember, the pole where magnetic field lines enter a permanent magnet is the south pole. The pole where lines leave the magnet is the north pole. If magnetic charges existed, then magnetic field lines could start on isolated north poles and end at isolated south poles, just like electric field lines start on positive and end on negative charges. But since magnetic monopoles have not been discovered, magnetic north and south poles always accompany each other. Another source of magnetism is so-called geomagnetism. The Earth has its own magnetic field. The configuration of the Earth's magnetic field is very similar to that of a gigantic bar magnet placed deep inside the Earth's interior. The Earth's magnetic field lines appear out of the ground near the geographical South Pole. This means geographical South Pole is actually magnetic North Pole. The Earth's magnetic field lines enter the ground near the geographical North Pole. In other words, geographical North Pole is the magnetic South Pole. There are several theories on how the Earth's magnetic field is generated. Most likely, the Earth's magnetic field is created by convection currents in the Earth's core. Charged ions or electrons circulating in the liquid interior could produce a magnetic field, just like a current loop does. The Earth's magnetic field is very important. It protects the Earth from high energetic cosmic rays. Typical values of various magnetic fields are shown in the table. The Earth's magnetic field is approximately 100 times weaker than the field of a bar magnet. But since the field is much extended in space, it has enough time to deflect charged particles to the poles. Deflected charged particles bombard atmosphere at the poles. And famous northern or southern lights, or so-called aurora borealis and aurora australis, can be observed.